Hi, in this video I am going to talk about CUDA streams. CUDA streams can play an important role in accelerating your application. A CUDA stream is a queue that contains GPU operations. These operations might be copy data from the host to the device, or copy data from device to host, or launching kernels. In this code I will show the differences between the default streams and the non-default streams. First of all, we have two kernels. The first one is add2. It takes an array as an input, and this GPU function will add 2 to every element in the input array. And notice that the length of the array defined here for every array in this code, which is 2 to the power 26. The other function, or the other GPU function, is multiply by 2, which will take an array and multiply each element in the array by 2. Here we have initialize data function. This function takes a host array and initialize every entry to some value. First function is the default stream. In this function we will see how launching kernels by default will use default streams. First of all, we need to define the number of bytes for each array, which is n multiplied by size of float, because the type of our arrays are float. Here we define two arrays on the host side using the cmalloc API. We pass it the number of bytes, and we cast the void star into our type, which is float star. So we have host data 1 and host data 2. Then we use initialize data function to initialize both arrays on the host. Then using CUDA malloc, we need to allocate two corresponding arrays on the GPU side, device data 2 and d data 1, d data 2. Then we need to copy the initialized data from the host to the arrays on the GPU. We use CUDA memcopy API to do that. The destination is the device array and the source is the host array. We pass it the number of bytes and the direction, which is from host to device. We do this for both arrays. And here we need to launch the two functions, the two kernels. Here we have the number of blocks and the number of threads in each block. We first of all call the add2 function, and we pass it the first device array. Then we call or launch the multiply by 2 kernel, and we pass it the second device array. CUDA device synchronize. We will wait until the GPU finish the execution of everything above. After that, we need to copy the result back from the GPU to the host. So the destination is the host data 1, the source is the device, and the direction is from device to host. We do this for the two arrays. Then we need to clean the arrays on the host using the C-free API, and also we need to clean the memory on the GPU using CUDA free API. Let's compile this code. Remember, in the main function we called only the test default stream, which is the function that we just explained. Alright, the function ran without any error. Now let's profile this function using NVIDIA Insight system. So here we use the command nsys, and we tell it that we need to profile, and we give it the path for our executable. Now it will run, the tool will run this executable and generate profiling report. The report name is report 1, and in order to visualize this report we need to use the Insight System UI. Call the report. The UI shows information about the CPU threads and the GPU CUDA. Let's look into the GPU part. As you can see here, by zoom in here, we have the memory copy from the host to device, and then we have the add to function, then the multiply by 2 functions, then we have the copy from the device to the host here. And you notice, because when we launched our kernel, we did not mention anything about streams, and in this case the default streams will be used, and as a result we see in the GPU all the GPU operation are executed in sequence, because this is timeline. And the first of all, the copy for data from host to device happen, then adding two kernel executed, then multiply by 2, then copy the data from the device to the host. This is because our kernels were run on using default streams. Now let's move to non-default streams. Again, we need to allocate 2 arrays on the host side, but this time instead of using the cmalloc API here, we will use the CUDA host allocate API with this flag in order to allocate an array on the host side. And the difference is that this API will allocate what is called binned memory or paged locked memory, and this memory will not be transferred from the memory using virtual function using the CPU. So this memory will stay and will not be paged. So this is why it's paged lock, and this is important because later on we will use the CUDA mem copy async API, and it's required that the type of the memory is pinned memory or paged locked memory. So now we have 2 arrays allocated on the host side, and we need to initialize these 2 arrays using our function initialize data. Then we need to allocate 2 arrays on the GPU side using CUDA malloc API. Now, in order to use the non-default stream, we have to create 2 streams. One will be used for each kernel. We'll use CUDA stream API or data type to declare two streams, stream 1 and stream 2, and we'll use CUDA stream create function. We pass the reference to each stream in order to create these two streams. Now here we will use CUDA mem copy async, and remember in the previous example we used CUDA mem copy, but here we use CUDA mem copy async API, which is asynchronous operation. It's just push this operation into stream 1 and it will return directly, and later on the GPU it will be executed on this queue or this stream. Now we will do the same for the other array. We will copy the data from the host to the device using CUDA mem copy async, and we pass it the second stream. Then we will launch the two kernels again, but now each kernel we will pass it the proper stream. For the add2 kernel we'll pass it the stream 1, and for multiply by 2 we'll pass it stream 2, and this means that add2 will be executed on this stream, or will be pushed on this stream, and multiply by 2 will be pushed on stream 2. Note that this third parameter 0 is not related here, but we have to add it in order to pass the compilation. This parameter is related to shared memory in the kernel, and we are not using shared memory on both kernels, so this is why we pass 0 here. For each function, as previously mentioned, we pass the proper array. For add2 we pass data1, for multiply by 2 we'll pass data2, device data2. Then again we will push more operation onto the stream 1, which is data, which is mem copy from the device or from the GPU into the host. See the direction here, from the device to host, and again we use the asynchronous operation CUDA mem copy async. So this again will be pushed to this stream. Notice on each stream we pushed many operations. First copy from the device to host, then from host to device, then launch the kernel, then copy back from the device to the host. In the stream itself, the operation will be executed on sequence, while in two streams they will be executed on parallel. Then here we will wait for each stream to finish its execution by calling the CUDA API CUDA stream synchronize for each stream. Then here we will free our page locked memory on the host using CUDA free host, not the free method, because we here use CUDA host alloc. Then we have to call the CUDA free host for the host to free the data from the host side, and CUDA free to free the two arrays on the GPU. Then we need to destroy the both streams that we created above, stream 1 and stream 2. Let's now compile this application, or before we compile, let's call this function from the main. So from the main now we call the test non-default stream. Alright, let's profile this application again. And see now report 2 generated. So in our UI or the GUI we will open the report 2 and let's see the CUDA section. As you can see here, our two streams mentioned here. Notice when we use the default streams, the GUI does not mention the stream name because by default it's default stream, while when we created or defined our stream 1 and 2, it's mentioned here, and they are giving these indexes 13 and 14, and you see stream 13 is responsible for the add2 kernel, stream 14 is responsible for multiply by 2 kernel. And notice that this is our timeline and there is an overlap in the execution of, first of all, the memory copy with the add2 kernel, and also there is an overlap between multiply by 2 and the add 2. It means that these operations executed in parallel, and also the same when copying back the memory from device to host, it overlaps with multiply by 2. So there are many overlaps in many operations, and this will accelerate our application. Notice also that it's impossible to have overlap between copy from device to host operation. This is why they are executed in sequence, and also from between two operation, between two copies from host to the device, they are in sequence. While it's possible to have operations parallel when we have two operations from when we copy from, let's say, from the host to the device and device to host. So it's possible to have them running on parallel, but from the same direction. We always have this sequence even if it's in different streams. So our functions are executed on parallel on the GPU. Now let's try to measure the execution time for both the default stream function and the non-default. I'll use the simple chrono library to measure the execution time. Let's compile again. Now the two functions are called, and for each function we will measure the execution time. So using default streams, it takes 3000 milliseconds, and using non-default streams it takes 1800 milliseconds, and this shows that using the non-default streams accelerated our application because most of the GPU operations are running in parallel. Alright, now let's move to the other example, which is blocking streams. In this example we will see how using default streams beside non-default streams can block some of the operation to be run in parallel. First of all, let's implement the non-default stream similar to what we did before. Here we use only one kernel function, multiply by 2, which takes an array, and it will multiply every entry in the array by 2. and here we have initialize data. Uh, it's used to initialize a host an array. So for every entry it will assign some value. Alright, first of all we need to allocate three arrays in the host size as the host data 1, data 2, data 3, and to do that we will use again the CUDA host alloc instead of the C malloc API. We use this as we said previously when we do copy asynchronous mem copy asynchronous, we need the type of memory to be page locked memory that's guaranteed to not be used in virtual memory. So this memory will be stay in the memory, and the CPU will not do any paging for these arrays. So we here again we use CUDA host alloc, and with this default parameters we pass it the name of the pointers and how many bytes. Then we initialize these three arrays on the host side. Then using CUDA malloc we need to allocate three arrays on the GPU side, and because we are going to use non-default streams and asynchronous operation, we have to create three streams here, stream 1, stream 2, stream 3. Each stream will be responsible on launching one kernel. So using CUDA stream data type we define three streams, and using CUDA stream create API we will allocate these three streams. Then we need to copy the data from the host to the GPU using CUDA mem copy async. Remember, this is asynchronous operation. At the moment the host call it will return. It will so what it does, it's push a mem copy operation to a stream, in this case stream 1, in the second for the second data stream 2, and for the third data stream 3. The direction is from the host to the device. Here we will launch the three kernels, or we will launch multiple by 2-3 times. Every time we will use different streams. So the first one will use stream 1, the second one will use stream 2, the third launch will use stream 3. And so this call, for example, will push launch kernel operation into this queue, and we pass the proper array for in each case. Then after the stream finish all the execution above, we need to copy the result back using again CUDA mem copy async, and the direction from the host to the device, and we will use the proper stream. So stream 1, now it has three operation: copy from host to device, execute kernel, then copy the results back to the host. This is also for stream 2 and for stream 3. Now we need to wait for the three streams to finish their execution using CUDA stream synchronize API. Then we need to free the three arrays on the host side using CUDA free host API. Then we need to free the GPU memory using CUDA free. Then we need to destroy the three created streams. Let's compile this code. So because here we use the three streams, we expect kernel to be run on parallel. Let's profile this code. Profile, give it okay. Our report number is 3. We will use the GUI again to visualize our report, and we look at the CUDA part. As you can see here, we have the 3 streams. These indexes are from the GUI, so what is important is we have 3 different streams that we created, and as expected we see these the 3 functions or the 3 kernels executed in parallel. Now let's do this change, make one of like this, the second one, the second launch of the kernel. Let's run it on default stream instead of defined stream number 2. So here we are telling CUDA that this kernel will be launched on the default stream. The first one in stream 1, the third one stay on stream 3. Let's compile again. Let's do profiling again. Okay, report number 4. Alright, we have here, see here stream 14 is not used. It's only used in the copy operation because I didn't remove it from here. So I created stream 2 and I did some mem copy to it, but I did not use it in execution, in any of the kernel execution, so you can ignore it. So we have 2 streams here, and we have the default stream, and as you can see the 3 kernels are executed in parallel. This is the first one, this is the second one, this is the third one, and this is because we changed the second launch to be executed on the default stream. Even though we have 3 different streams, the kernels are executed in sequence rather in parallel. The issue is that when we use this CUDA stream create, this is kind of blocking when we deal with non-default stream and default stream in our program in Mixed. So to solve this issue, we can use this API, CUDA stream create with flags, and tell that this stream is non-blocking. Because what happened right now, this is blocking, the default one is waiting for this one, so the 2 streams are blocking, and this also stream 3 will wait for the default stream, and so the 3 of them will be run on sequence. Now let's change for example stream 3 to use this create method, CUDA stream create with the flags, and let's leave the kernels as is, stream 1 default and stream 3, and let's see the results. We'll profile it again. Report 5. Right, as you can see here, number stream, the stream 13, stream 15 are running in parallel, and the default stream then will be executed. This is because that we did this using CUDA stream create in the third one, and this will tell that this kernel, this launch, don't wait for any of the two, so this one will be executed in parallel with this one. Then this one, it's still the default stream, and as we said, the default stream also will wait for the stream that created using create stream create, which is stream number 1. Now let's also use this API for stream number 1. Now we have CUDA stream create with the flags non-blocking for also stream number 1. Let's profile it again. Report 6, and we'll expect the 3. As you can see here, the 3 kernels are running on parallel. Alright, now let's move to the other example, which is default stream per thread. Imagine if we have or assume we have C++ threads and 8 threads, and each thread is responsible of launching a kernel. So this is our launch kernel function. Again, we'll use some kernel function. Here I use square root kernel, so it will take an array, and for each element on the array, this function will do square root. This is initialized data helper function. In the launch kernel function, that will be run on the CPU thread. So for each CPU thread, we will launch the kernel. Once we allocate an array and we initialize the data on the host array, then we create corresponding data on the GPU. We copy the initialized data to the GPU, and here we launch the kernel using the default stream. Then we will wait for the stream, which is 0 here, the default 0 means the default, to finish the execution of the function square root. Then we will return or we will copy the result back from the GPU to the host, and we will free the memory from the CPU or from the host, and we will free the memory from the device. Notice here we use the default stream in every thread. So for every thread we are running launch kernel, and even though each thread has its own launch kernel, the behavior is all the threads in the GPU or all the kernel will be executed on sequence. Let's compile this code and profile it. streams. Alright, let's profile this executable. Report 7. As we expected here, you can see in the timeline that the 8th thread in the GPU, the eight kernels are executed in sequence. This is in addition to the memory operation, so everything is running in sequence, and this is when we run, or when we use the default stream in each thread, even though the launch of the kernel is done separately on different threads. In the GPU side, these kernels will be running on sequence because they are pushed to the same stream, which is the default one. Now you can change this behavior by compiling using this flag, which is dash dash default stream per thread. This will tell the default stream in every thread will handle things separately. And so we have default streams for each thread. Let's run, and you see the execution time already dropped significantly, because right now every thread will has its own default stream. Let's profile this code. Report 8. As you can see here, all 8 threads are running the functions in parallel rather than in sequence, and that's because we change the behavior of the default stream per thread when we compiled using the dash dash default stream per thread options.